Geometry lesson 4-6. Speaking specifically about the isosceles triangle, we want to make sure we have some of the pieces of it understood. We have what we call the base of the isosceles triangle. We have two legs that will be exactly the same. The base of the triangle is the one that is not congruent. Even if this triangle were turned onto its side so that it appeared as if it were sitting on one of the legs, we would still consider the base to be the angle that, or the side that did not have any other side in common. We have what we call base angles. The base angles connect to the base. They will always be exactly the same. Base angles will always be congruent. And the opposite angle away from this is what we call the vertex angle. So we have a vertex angle and two base angles. We have two legs and a base. And that represents the three sides and the three angles of the isosceles triangle. The base angles theorem. Now this has to do again with isosceles triangles. If two sides of a triangle are congruent, just like the base angles were, then the angles opposite them are also congruent. So two sides, if we go back to that, that's saying these right here, two sides, then the angles opposite of them, meaning this angle and this angle, because they are the ones that are opposite, will also be congruent. So here we have a situation where we have an isosceles triangle, and I'm stating that if A to B, line segment A to B, is congruent to A to C, then the sides opposite of them, in other words, this angle here and this angle here, will be congruent to each other. Angle B and angle C will be congruent. That's the base angles theorem. So the moment you know you're dealing with an isosceles triangle, you know you're going to have two base angles that are the same. The converse. Now remember, this goes the other direction. Converse reverses the order. So dealing with the same shape, if we now know that we have two angles of a triangle that are the same, then we know the sides opposite of those, in other words, going from here back this way and back this way, are going to be congruent. So if we know angles B and C are congruent, then we reverse that and say, oh, therefore the opposite sides will also be congruent. So it works with the theorem and the converse reversing it, forward and backward. Very similar to everything we've done in the past involving parallel lines, perpendiculars. Alright, corollaries. Remember, this is going to be based off of other easy-to-prove theorems. Corollaries to the base angles theorems and the converse. If a triangle is equilateral, and remember equilateral means all three sides are the same, then it's equiangular. And if a triangle is equiangular, then it's also equilateral. Remember that we also talked one day about how an equilateral triangle is also an isosceles triangle, because by definition you must have two angles that are the same and two sides that are the same to be isosceles. Well, an equilateral triangle satisfies that. It does have two, it just happens to have three. So when you're looking at an equilateral triangle, try to make this as equilateral as I can, you could say, okay, these two are the base angles and they're the same, so therefore this side matches up this side. But then someone might go, well, I think that these two are the same. Okay, well then that side has to match that side, and therefore you have a situation where all three sides are the same and all three sides are the same. In other words, it's an equilateral triangle. So it's okay for an equilateral triangle to be considered isosceles while you're working with it. Alright, so here's that equilateral triangle. Just remember, you might say here and here, therefore those two sides are the same. Then you might say, well, I think it's here and here, and so therefore the opposite sides would be the same. Still proving the same thing, all three angles, all three sides. Example number 1, a little tricky. You actually have two different triangles here. We want to find the values of x and y. We know we're dealing with an isosceles triangle because these two sides are the same, which means that angle and that angle have to be identical to each other. And if you know this one is x, it means that this one over here must also be x. And now all triangles equal 180 degrees, so x plus 50 has to equal the 180 degrees. Add your like parts. 2x's plus 50 now equal 180. We subtract 50. 2x now equals 130. We divide both sides by 2. And we have figured out that the x value is 65. 65 degrees. Now you might say, well, I don't understand why that's helpful. Well, in reality, this was an isosceles triangle. But this is also an isosceles triangle. And the reason I know, because that side right there, this leg, is going to be equal to that leg, which means this long side right here is considered the base. And if it's the base, the leg going there. If that's the base, then these two angles have to be the same, which means this is y, and that's also y degrees. And I can't solve this until I figure out what's on the other side of this x. But because this forms a linear pair, then whatever that is plus whatever this is must make 180 degrees. So I will take 180 degrees and subtract 65, which leaves me with 115 degrees. So this is a 115 degree angle. Now if you use some of your thinking in this and you kind of look at the numbers and how they work, these other two right here must add together to make that 65, which is really kind of interesting. Remember, the exterior angle is equal to the two non-adjacent interior angles. That was something we learned a few lessons back. The exterior angle of this triangle is always equal to the two non-adjacent interior angles. In other words, you could say 2y plus 115 is equal to 180, but what's going to happen is you're going to subtract that 115. You're going to create a situation where 2y equals 65. Remember, this angle is equal to the two non-adjacent interior angles. Divide by 2, and y equals 32.5 degrees. So we have now solved for both x value and the y value, all based off of the base angles theorem. Up to this point, you should have 4 different ways that you can check congruency for triangles. We have side, 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 which we learned the first day, as well as side, angle, side. And what's important is the side and the angle and the side, the two sides must form that angle. So the two sides are coming together to form this angle. That angle is in between the two sides. And then we have angle, side, angle, where the two angles have a side in between them. So the two angles are on the edge, and there's a side that's in between the two angles we're talking about. Or we have angle, angle, side, and this time the side is not in between. So it's angle, angle, and then a side somewhere. But it must correspond to another triangle's same location. I'm going to add one more, known as the hypotenuse leg theorem. Now if it's a hypotenuse leg theorem, the fact that it has hypotenuse means it must be a right triangle. And so we're dealing with right triangles in this case, and we would say if a hypotenuse and a leg, that's only 2 pieces. Basically it's two side lengths of the triangle. If a hypotenuse and a leg of a right triangle are congruent to another triangle's hypotenuse and a leg of the second right triangle, then the two triangles are going to be congruent to each other. In other words, this scenario here. I don't care if it's this leg, it matches up with that leg, or if it was this leg and happened to match up with that one, it just means that the triangle has been flipped. What's key is you must have the hypotenuse and the hypotenuse be the same, and then you have to have a leg that's the same. Since it's a right triangle, you really have a situation where you have 2 sides and an angle in reality. Okay? So you have 2 sides and an angle. So it's kind of similar to these, but it's not in the exact same order, but it'll always work with right triangles. So you could add to this list the HL, hypotenuse leg theorem. You have these 4 involving sides and angles, and you have this one only for right triangles involving the hypotenuse and the leg. Alright?